Hey everyone, thanks for joining and thanks to the GMPV ECS committee for the opportunity. So today I'm going to talk about some climate modeling work that I did recently to try and understand how climate change and volcanic eruption interact. And before I start, I want to highlight that this is very much a collaborative work with my co-authors from University of Cambridge and the UK Met Office. So the motivation really for this work is first that volcanic eruptions and volcanic aerosol impact climate by decreasing the atmospheric transparency and cooling the surface. So what happens when you have an explosive volcanic eruption? There's a plume of ash and gas that rise in the atmosphere and inject SO2. And in particular, we really care whether that plume rises above the tropopause into the stratosphere, because that's where sulfate aerosol have a long lifetime and long-lasting climate impact. So this SO2 gets converted into aerosol, they grow in size, they get dispersed all over the globe. And the main effect of this aerosol is to scatter some of the sunlight, including some that get scattered back to space, which result in this increased optical thickness of the atmosphere and surface cooling, as well as impact on the hydrological cycle and major climate mode of variability, such as the El Niño oscillation. And after 1 to 2 years, these aerosols settle back to the troposphere, where they get washed out by precipitation. And so if we look at the global mean stratospheric aerosol optical depth since the beginning of the satellite era, that's how this time series looked like. And each peak on this time series is essentially a volcanic eruption. In particular, the two biggest peaks here are the eruptions of El Chichon in 1982 and Pinatubo in 1981, which had volcanic explosivity index of 5 and 6. But what you really care about is how much sulfur dioxide, SO2, they injected, so on the order of 10 teragram from this eruption. And if you look at the more recent period, the beginning of the 21st century, it's characterized by a lot of moderate magnitude eruption, which had VEI of 3 to 5 and injected more on the order of 1 teragram of SO2. But you can see that these are associated with a lot of peaks. So of course they are smaller, but they're also much more frequent. Now, that's for volcanic impact on climate. The question I really want to discuss today is the opposite question. How is climate change affecting volcano and volcanic forcing? And so if I go back to my cartoon, there are various processes that can be affected by climate change here. So starting with eruption source parameter, it's been known for quite a long time that ice sheet retreat and advance, as well as hydrological cycle, can affect volcanic eruption, and in particular how frequent they are or how big they are, as well as the eruption style. A pool of climate volcano feedback that's been recently discussed is what's called internal climate feedback. And the idea here is that even if you apply the same volcanic forcing, meaning the same reduction of incoming sunlight, you will get different climate response if the background climate is different. And that's related, for example, to change in the ocean stratification. But I would argue that before looking at this kind of feedback, the key question is to know how the forcing is going to change itself. And for that, we look at subaerial volcanic processes type of feedback. So all the processes that happen in the atmosphere, you could argue, are the most obvious feedback because they are directly sensitive to changes in the atmospheric condition. And in particular, the plume rise may be affected by changes in atmospheric stratification of wind, which I've shown during my PhD. And then the sulfate aerosol chemistry, microphysics, and transport, that's directly dependent on climate. And yet, until now, it was a mostly unexplored pool of climate volcano feedback. So that's the type of process I'm going to focus on today. And so to discuss how these processes will be affected by climate change, I'm going to use two types of model. The first type is a one-dimensional volcanic plume model, which essentially can predict the height at which SO2 is injected by an eruption, being given two critical inputs: the mass eruption rate, so the flux of ash and gas that comes out from the vent, and atmospheric profiles, such as the temperature profile at the volcano and the wind profile. And then the second type of model is what's called an aerosol chemistry climate model. And essentially, it's a climate model that can also has the capability to predict how volcanic SO2 gets converted into aerosols and how these aerosols affect Earth's radiation and climate. There are mostly two kinds of input to this model. One broadly is what I would call the background climate forcings, and that includes things such as how much energy we get from the sun or how much anthropogenic greenhouse gas emission there are. And then for a specific problem, a particularly important input is just the SO2 injection. So how much SO2, where, and how high are injected by volcanoes. And then these two models, we make them communicate in the following way. So I just say that the height of the SO2 injection is needed in the climate model. That's going to be provided by the one-dimensional volcanic plume model. And the one-dimensional volcanic plume model in turn needs atmospheric profiles, and these are going to be provided by the aerosol chemistry climate model. So that's how we make them talk to each other, if you want. So then using this combined modeling framework, we run 3-year-long simulations of a volcanic eruption occurring at the location of the Mount Pinatubo volcano. So I just want to highlight that it's a tropical volcano. So I'm going to be talking about tropical eruption. And then we've been looking at 2 different climate scenarios. So our kind of reference climate scenario is the late 20th century using the historical set of forcings. So that's a good characterization of a present day. It's not present day anymore, but recent climate. And then a warm climate scenario is going to be the 2090-2100 climate projections for what's called the SSP5 8.5 scenario. And that's the upper greenhouse gas emission trajectory, anthropogenic greenhouse gas in climate projections. And in addition to looking at 2 climate scenarios, we also look at 2 different eruption case scenarios. So the first one is a moderate magnitude eruption injecting 1 teragram of SO2 and with a mass eruption rate of 10 to the 6 kilogram per second. And then we look at a large magnitude eruption for which eruption source parameters are essentially scaled by 1 order of magnitude. And then for each combination of climate scenario and eruption case scenario, we run 10 different simulations which sample different initial conditions, for example, in terms of the atmospheric profiles simulated by the climate model, because that's going to ultimately affect plume height and result in different forcing and climate response. So that's it for the experimental design. So I'm going to walk you briefly through some results for the moderate magnitude eruption, starting with how the SO2 injection height or the plume height differs between the 2 climate scenarios. So the y-axis on this graph here is the SO2 injection height. The x-axis I won't talk about much today is the quasi-binaural oscillation phase, which affects the dispersion of aerosol. And then all the blue dots here are the height over 10 simulation for the historical relatively cold climate. And the dashed line here is the tropopause. So you can see that we chose a mass eruption rate that results in a plume height roughly at the tropopause level. And that's consistent with many of the recent moderate magnitude tropical eruptions, for example, Nabro 2011. And then if you look at the red dot, so that's for the 10 plume height of the future climate, you can see there is more variability in plume height, but on average, you still get a plume height of roughly 16 kilometers, except for these 2 simulations here. So really here, climate change doesn't affect the plume height too much for this moderate eruption. But what's really changing though is the height of the tropopause, which is the dashed line here, which increased by almost 2 kilometers. Because the troposphere is warming and thus expand. And what that means is that in the future climate, this moderate eruption inject much less aerosol directly into the stratosphere. So they would need to be more powerful to reach the stratosphere. So now if we look at the consequences in terms of stratospheric aerosol optical depth, that's how it looks like. So that's the global mean SAOD time series for the first 3 months after the eruption. So that's now output from the climate model. The blue line here is the historical climate, and the red line is the SSP 585 climate, the relatively warmer climate state. And you can see a huge decrease of the SAOD perturbation in the future climate by a factor 4 for the peak perturbation, which is essentially driven simply by the fact that volcanic plumes don't reach the stratosphere in the future climate, which means that ultimately there is less stratospheric aerosol and a smaller stratospheric aerosol optical depth. And then that suggests that in the future, we could expect a decrease of what's called the stratospheric aerosol background. And this relatively small background has still been shown to be associated with a significant footprint in terms of radiative forcing and surface cooling. So that's it for the moderate magnitude eruption. Now, if we look at result for the large magnitude eruption, again, I'm starting with what's happening with the SO2 injection height. If you look at the blue dots, again, our historical cold climate, we picked a mass eruption rate so that the injection height was roughly at 21 kilometers, which is consistent with observation, for example, for the Pinatubo eruption for the SO2 cloud. Now, if you look at the red dot, the future climate state, you can see they are all much higher. So the injection height increased by roughly 1.5 kilometers. And that's related to a decreased stratospheric stratification in the future climate, which make it easier for the volcanic plume to rise in the stratosphere. And so because now we have different plume height, in addition to running just one set of simulation with the historical climate and one with the future warm climate, we run a third set of simulation, which I'm going to label SSP 585HIH, where we use the warm climate in the climate model scenario, but we use the injection height from the historical climate. And the aim of that is just to disentangle the effect of changes in plume height versus changes that, for example, affect atmospheric circulation. Okay, so again, now we are looking at the response of the SAOD, the stratospheric aerosol optical depth for the large magnitude eruption for the 3 years following the eruption. The blue line here is still the historical cold climate, and the red line is the future warm climate. But now the orange line here is when we run the climate model using the SSP 585 scenario, so high greenhouse gas concentration, but where we use the SO2 injection height from the historical climate. And so what you can see is that regardless of the which injection height we use, we have a strong increase of the SAOD peak by roughly 10%. But then if you compare the orange and the red line, you can see that the orange line decay much faster. So that means that when we account for the increase in SO2 injection height driven by climate change, we have a slower decay of the SAOD perturbation. And now if we look at the corresponding time series in terms of top of the atmosphere radiative forcing, so that's really the energy now that's removed from the Earth system. That's how our simulation look like. And in particular, you can see that the red line here has a much stronger peak radiative forcing compared to the blue line, so the historical climate. And there's indeed a 30% difference here. So this 10% difference in optical thickness results in a 30% difference in how much energy gets removed from the Earth system by the volcanic eruption. And last, if you look at the temperature response corresponding to this simulation. So first I'm showing you the stratospheric temperature. So in the stratosphere, because the aerosol absorbs sunlight, the response there is a warming of the stratosphere. And so the light shaded bar here show you the warming for the first post-eruption year, and the most strongly shaded one is just the average over the first 3 years. So you can see that this stratospheric warming gets stronger in the future climate scenario, and that's even more true when we account for change in plume height. It's really a big difference, an increase by 60% of how much the stratosphere gets warmed by volcanic aerosol. And then if you look at the surface air temperature response, which is what matters for most humans, here the signature is a cooling, which is expected because you remove some energy from the Earth system. And again, you can see that this cooling footprint becomes larger in the future climate when Earth is warmer. And that's a roughly 13% difference with the historical reference scenario. And so the key question here is whether we expect increased volcanic cooling as Earth gets warmer, which would be a good news. So to summarize our main conclusion, the main takeaway I want you to get is that subaerial volcanic process such as plume rise and the aerosol cycle, they are all sensitive to climate change, and they represent a key pool of climate volcano feedback. For large magnitude eruption, we project an amplification of the forcing and temperature response. But it's a complicated story because we project exactly the opposite for moderate magnitude eruption, which are smaller, but they are also more frequent. And so as usual, volcanoes do not make for a very simple story. And then just want to share some outlook. So one of the things we really want to do is test whether we get a similar result using different climate model or plume model. And also I've only been talking about extratropical eruption, tropical eruptions, sorry, and we need to look at what's happening for extratropical eruption. And last, I've been talking about subaerial volcanic processes today. It would be really interesting to understand how feedbacks related to these processes would combine with eruption source parameter feedback and the internal climate feedback, because really this combination is what's going to determine the fate of volcanic cooling as Earth is warming. And then last thought, as this is an ECS talk, so as a volcanologist, it was pretty cool to cross the line and go do climate science. I think it enabled me to diversify my skills, for example, with climate modeling. It was just really cool to work at the crossroad of climate and volcano. And I think there's lots of work to be done. And that's it. I'm happy to take any question.
I've got a quick question while we're kind of waiting for people to put some answers in the chat box. Have you looked at sort of the effect on the tropopause, sorry, in more polar regions? Because it's, well, my understanding is that it's much lower there, and how would volcanic eruptions in sort of more northerly or southerly latitudes, how would that affect the tropopause?
Yeah, so that's a good question. So I've been looking about it in terms of plume modeling, but I haven't performed any combined plume climate modeling simulation. So you are right that the tropopause is smaller there. The tropopause is still projected to increase. So some of the effects I discussed are still true, but that increase is smaller. And even more importantly, in high latitude region, the plume height is really sensitive to the wind on the day of the eruption. And so what really matters there in terms of is the plume height going to reach the tropopause height, is our wind pattern are changing.
And then I've got another question, if that's all right. If we've not got any ones in the chat yet, but just with your you say the overall cooling of the surface temperature in the sort of year 1 to 3, how is that a kind of overall how far have you projected that? Like, does that is that going to see like a continued cooling, or is that kind of a blip of cooling and then it'll go back to warming? Like, how it's like quite good news, but obviously, like, how long is that going to last?
Yeah, so I mean, essentially, if you look again at the SAOD and forcing time series, the time scale for the cooling is roughly the same time scale as the SAOD decay. So it's a 2 to 3 year cooling for large eruption. Some very large eruption have extended cooling because they affect the ocean, and so that extend the signal. But the main cooling is on the order of a few years.
Okay. Yeah. Okay, right. So we've got some messages now. A question from Emily. Could you comment on the uncertainties associated with these models?
Yes, I can. Essentially, they are large. So I guess anything volcanic has large uncertainties anyway. What I can say is that in terms of plume modeling, I was able to do a lot of sensitivity tests before combining with the climate model. And the projection of plume height increasing in the stratosphere is very robust. It's also very robust that the tropopause height is increasing in the tropics. We can actually observe it. So the plume height part, I think, is quite robust. Then the aerosol cycle and climate modeling part, that's where we really want to go compare what other climate models are projecting. So yeah.
Brilliant. Then we've got 2 more questions. So this says, I'm wondering if you could speculate about the implications that we may expect in the future of the climate change scenario approaches SSP 585 in terms of hazards. Could the eruptions become more hazardous or less hazardous, especially with the thermal effects?
Okay, I'm not sure what's meant by the thermal effect, but essentially speculating in terms of what's the net effect of climate-volcano feedback is a bit hard for the moment because we have this increased cooling for large eruption, but this decreased cooling for small eruption. So really this work is kind of a first stone just to understand physically what's happening to each class of eruption. Where we need to go next is to kind of do a longer term climate simulation with a realistic distribution of eruption of all sizes and see how their net effect on climate is affected by greenhouse gas emission. So that would be our answer. And in terms of hazards, I guess there would also be interesting thing to do about how climate change affect, for example, ash dispersion and whether the, say, future disruption to transatlantic aviation route would be affected by changes in wind pattern or such things.
Brilliant. There's a few other questions, but I was wondering, just to keep time moving on, would you be able to answer those in the chat? And then, so yeah, feel free to continue to ask questions, and the speakers can answer them in the chat as well.
Perfect. Thanks a lot.
Brilliant. Thank you very much.
Great, thanks, Thomas. So our next speaker is Ines Tomaszek. And so I'll give Ines a quick introduction, but if you want to start sharing your screen. So Ines is a medical geologist working on volcanic health hazard assessment using multidisciplinary approaches and methods.